All right, this is the start of the recording. It is about a minute before 8:50 a.m. on Tuesday, April 28th. All right. Okay, welcome folks. I'll move this on over to the other screen and do that. I'm going to move a couple things around here so that I can. All right, there we go. Yeah, sorry about that. There's a lot of things I need for today. So, okay, um, forgive me if I kind of use this pen wrong. I had an issue in my 11 o'clock class yesterday, so I'm trying a different pen because I think there was a battery issue. But I'm getting used to where the buttons are located, so hopefully I can do this right. Anyway, today's Tuesday, online quiz. No online quiz Thursday because there's an online exam, right? So for that, there's the math is a process pre-exam assignment. Somebody had commented that it was the instructions weren't posted, so I did post those. Sorry about that, but the instructions are the same as previous times. It's just a chance to kind of inventory for yourself what things you'd like to go over and what's your plan to go over those things. Thursday is the official date of the exam, but again, recognizing the kind of timing that people have and schedules maybe kind of all shifted around, you pick a 5 hour block of time of your choice on Thursday or Friday. And the intention isn't to take all 5 hours, but the point is, I hope you'll take an hour, maybe just a little more, to work on the exam. To perhaps, if you'd like to write out your answers, you can do that, and then use an app like that. I did mention several options of free apps for phones where you can take multiple pictures and then put them all together into one file. And the app, there are free apps. No need to pay for an app. It will create for you a PDF, and then it would be possible for you to just look at that PDF, make sure everything's clear in one file in order, and then once that's set, you can upload that one file. So I hope that process simplifies your workload and gives you sort of a bit more guarantee of you're like, okay, did I turn in all the things? Well, you're turning in one file, so you can look at that file before submitting it and make sure. Um, Please keep current with web work. That would mean starting web work 40 would be about ideal today. Again, sometimes what happens is people fall into this kind of habit of just starting the assignment that's due on a particular day, and that will you run into a lot of frustration with that. Avizaras are again listed here for as a reminder. Yesterday we said this. I'm going to just say this in slightly more detail. Is that given a function y equals f of x, and given x values a and b, the this new thingy that we started yesterday called the definite integral. It is the signed area between the graph of y equals f of x and the x-axis, and then two other things. But let me pause there first. The x-axis, so that's a horizontal line, and then the graph of y equals f of x. Well, like in this picture, I'm just here's my cartoon version. There's the graph of the function. So this is it's the graph of a function should pass the vertical line test. So this is kind of morally it's a horizontal thing, right? Like it goes up and down, but it's sort of it can be completely horizontal, it just can't be completely vertical. And so you have sort of these two horizontal pieces, and you have to think of we have to cap these off somewhere, otherwise when does it stop? So the two vertical lines, x equals a and x equals b, help cap off things. So in this picture, so yesterday you saw three kind of cartoon pictures of this definite integral, which was a signed area. Here's a new picture, a fourth picture. And in this picture, from x equals a to x equals b, there's actually three regions. So there's a positive area right over here, a big piece. There's a medium-sized region over here that's also a positive area. And then down here, there's this tiny, tiny sliver right in there. Let me try to fill this in solid. That's below the x-axis, and so there's this tiny little bit of negative area. I know it's a little strange to talk about positive area and negative area, but doing it this way is what's going to make what we do tomorrow and then Monday after the exam. It's going to make everything kind of fit together and work. Okay, so in this example, anyway, there's three different regions, but two of them are rather large positive areas, and there's this one tiny negative area. So overall, we would expect for this one, the definite integral should be a positive number. So I have two more, like this is, the cartoon is kind of good to look at, but I have more concrete examples. One of them looks a lot like yesterday, and then one of them doesn't. So I'd like to look at the definite integral from x equals -1 to x equals 5 of the function 4x dx. So the function here, just to identify the pieces and fit it with what we just said generically a moment ago, the function in this example is f of x equals 4x, or you could say y equals 4x. The x values provided in the question are -1 and +5. So to match with the notation being used just a moment ago, generically that first x value is called a and the second x value is called b. And so I'd like to draw this f of x equals 4x, or in other words, y equals 4x. This, by the way, is a y equals mx plus b. So I don't even want to say b because b is being used for a different thing. So what I'm just trying to say is y equals 4x should be a line. The slope is 4. The y-intercept is 0. So it should look something like this, right? So then these x values of -1 and +5 are drawn in here. We are going to need these y coordinates. So where did the y coordinates of -4 and +20 come from? Well, so this point here, for instance, this is a point on this slanted line, right? This slanted line of slope 4. So because it's a point on the line, you can plug in this x value of -1, that's right there on the tick mark, plug that into the function. And that's where you get -4. Same deal, if you plug in this x value of 5 into the function, you get the y value 20. So that's where, so this point, it's on the line, right? X coordinate -1, y coordinate -4. This point is also on that slanted line, x coordinate 5, y coordinate 20. Right? So that's where the y values were not directly provided in the question, but we get them. And we need these because, well, there's, we're talking about signed area, so we need to find the area of these two triangles. First, the bigger triangle, shown in yellow, it's above the x-axis, so it's a positive area. So area formula for a triangle, 1/2 times base times height. So there's the 1/2. And then the base is 5. You see right here, it should be, if you start at the origin, and then you walk over to right there, that's drawing in a picture of the base, but that's starting at x is 0 and ending at x is 5. That's 5 units to walk towards the east. There's that base of 5. And then the reason we computed this y coordinate of 20 was we needed this height right here. But if you start down here in the lower right, that point is where the y coordinate is 0, and you go up to right here, the y coordinate is 20. This is a perfectly vertical line segment, so to find that distance, the length of that line segment is at the bigger y value minus the smaller y value, so 20 minus 0 will give you this 20 right there. The other triangle has a base of 1, so if you start at the origin, you have to walk 1 unit to the left to get to where x is -1, and then has a height of 4, because if you start here at this point, let me actually erase the rest of this. So if you start at this point, the height is found by walking down to this point here, but if you start at the y coordinate of 0 up at this point, up there, whoops, up here, then walking down 4 units down there, that should be, yeah, that's 4 units to start at y is 0 and then to end at y is -4. So here again, just leaving off all the minus signs for now, I just want to think about what the area is first, and then we'll tack on the minus signs as we need to. So here, 1/2, just in the 1/2 base times height formula. Then we have a base of 1 and a height of 4. Okay, so then we'll piece all these things together. To demonstrate how this equal sign really goes here, I took the original question, put a copy of it down there. So we have the positive area. So this 1/2 times 5 times 20 is written first. And then this 1/2 times 4 times 1/2 times 1 times 4 is a negative area. So that's why it's written after a minus sign. You can leave a final answer like this as far as I care, but just to really emphasize the point, this number ends up being 48. And we'll use that number at the end of class just for one other thing. Okay, so there's an example that looks like yesterday. I have a different example that does not look like one we did yesterday. It introduces its own new challenge, but I hope not too much. So here, the function. So I should read off the question. Integral from x equals -2 to x equals 13 of the function absolute value. That's the new thing, the absolute value of x minus 3. So the function here in this example is absolute value of x minus 3. If you prefer, you could write, of course, y equals absolute value of x minus 3. Well, what does the graph of that look like? Right. So we'll think of, bringing up maybe an obscure thing from an algebra class. I hope you had seen the graph of the absolute value function. Looks like a V shape, like this. That's the standard absolute value function. There's this 45-degree angle there, another 45-degree angle here. But then when you look at y equals absolute value of x minus 3, so this minus 3 that's directly applied to the x should be a shift horizontally, but to the right. Okay, so this sort of, you may recall that at the beginning of the semester I said that just about everything you look at in an algebra class comes up at some point in calculus, and I'm not just doing that for fun. That's kind of just how the nature of the thing goes here. So if this V shape shifts over 3 units, you should have a graph that looks like that. Now the slope of this piece is actually a positive one, and the slope of the other piece over here is a negative one, and because that slope is a negative one, this y-intercept right there, sorry, this is getting a little messy, that y-intercept actually has to be 3. So here's a cleaner picture of this, right? So this right at x equals 3, that's that vertex, and here, not that we need it, but just that y-coordinate on the y-intercept here happens to be 3. We will need the y values again in order to get the heights of these triangles. Now you'll notice because we had y equals absolute value of x minus 3, you never get negative y values, right? So I mean, y can't be, because the absolute value of anything is always positive, or maybe 0 at the smallest. So when is y the smallest, or when is y equal to 0? It's when you plug in x as 3. And that's in fact another way to get this graph. If you don't remember this graph transformation thing, you got to be careful right around when x is 3. So I would actually do something like this. Pick numbers around 3 for x. I mean, this is not the way I suggest you do it. Whoops, that's not even a 3. That should be a 2 there. This is more time consuming as an approach to graph, and it's prone to errors, but it, can get you started, and it should build this graph for you. But in any case, okay, so there's this V shape, and then because all the y coordinates are positive, right? So that's why I didn't draw much down here. I kind of focused the picture where the axes are located to avoid having to draw too much that's below, because nothing is down there. Where did this y coordinate of 10 come from? Well, you plug in x is 13, right? Absolute value of 10 is 10. And then where did this 5 come from? Well, when you plug in x is -2 right here, you have absolute value of -5. Again, remember it's absolute value, so you end up with a positive 5. And just as we said, all the y coordinates here are positive. So here's a complete picture with apologies to you if you're a Vikings fan, I guess. Sorry, just things happen here, color-wise. So yeah, there's that discussion of where did these y coordinates come from. You take the function, you plug in the 2x values, get the y values. And that's helpful because now this triangle right here, the smaller green triangle, has a width of 5. This distance here, again, across the bottom, to get that base, it's bigger x minus smaller x, right? So we discussed this idea of a horizontal distance before. It's the bigger x value of 3 minus the smaller x value of negative 2. So 3 minus negative 2. This distance is 5. And then the height is also happens to be 5, right? Because you start down here and then you end up right there where this 5 tick mark is. So 1 half times 5 times 5. And then this other triangle over here, well, the base is 10, right? Starting at 3, walking to the right, right till right there. Starting at 3, walking over to 13, that's going to take 10 units of walking. And then starting at this point in the lower right corner and then walking up, that's going to be 10 units, so a height of 10. So base of 10, height of 10, so 1 half times base times height there. Putting this all together, both, unlike the last question, we had 2 triangles, but one was under the x-axis before. In this case, both of these are above. So we count both of these areas positive. There's no minus signs. Right, so 1 half times 5 times 5 plus 1 half times 10 times 10. Hope that's looking all right. What I'd like to do then, let me know if you have a question, but I'd like you to work on these. So I'm going to give you some time. In each case, these questions are about assigned area. Signed area, right? So for instance, the function is 5. That's a horizontal line, right? So the function here is y equals 5x. Here the function is f of x equals negative 2. Here's the function. I'll circle the function, in each of these. This last one's a little strange, so I'd start from the hint, but let's, get there when you get there. Those are the functions in each case. And then like the x values, right? So in the first problem, your x values are 2 and 12. In the third problem, your x values are 4 and 10. So you need to draw on some vertical lines. So in each case, draw a picture. And then look at area. So you'll be thinking about using the area formulas for triangles, rectangles, and for the last one, the area formula for a circle will apply. Draw pictures. Think about what areas should be counted positive, what areas should be counted negative. I should stop talking for a little bit. If you have questions, you let me know. just to make sure we're on the same page, I'm going to just draw out a quick picture for the first one of, there's my axes, and x is 2, x is 12, so you get these vertical lines, and then the function is just y equals 5. So it's not a very wavy function, right? It's just a perfectly horizontal line across. Different examples will have more details going on, but the region is that. It's a rectangle, height of 5, width of 10, right? So 5 times 10 or 50. That's what this first one should be equal to. If you want, you click on that first link just to let you know what you'd get yourself into. If you clicked on the link, it takes you to this where the region is shaded here in purple. And then you don't need to look at most of what's here, but when you click on these links, like this quote thing, I just tried to put some words to it. This rectangle has a height of 5 and a width of 10, the area is 50, and then final answer is shown here. So those links, I hope, will somewhat help. This second one, maybe just to say one thing, and then is, so the function here is 5x, right? So, okay, line of slope 5, the y-intercept is 0. So the line should go through the origin. You have a relatively steep line. Even in my picture, this slope only looks like maybe 2, but it'll do. X coordinates of 2 and 12. So I'm going to intentionally draw 12 here so that it doesn't spill off screen. So we can talk about the y coordinate there, and then 2. So plugging in, x is 2 to get the y coordinate into 5x, we should get a y coordinate of 10. When you plug in x is 12 into the function 5x, you should get a y coordinate of 60. There's two ways to view this. You could either think of this as a triangle plus a rectangle, or you can think of this as a big triangle minus a small triangle. So one approach, the triangle plus rectangle approach, is you draw this splitting line here, and then underneath this part is a rectangle. It's actually a square, which is a special kind of rectangle. And then there's this triangle above. That's one way to do it. The other view of this is a big triangle minus a small triangle. So the big triangle is starts at the origin, actually. Sorry, this picture is going to get a little messy. So those 3 points form a big triangle, but that's too much. That's too much region. There's that when you compute that big triangle, you end up counting the tiny little triangle down there, which you don't want to count. So you have to remove that. Here are the two pictures, actually. Maybe this will... Sorry, I lied. I was going to give you time to work on these. You'll have some time, but here's the first picture, right? So the first way of viewing... Let me turn off some of these things here. And so the region is this, right? And this purple region, you can... let me remove that purple coloring here for a moment. You can think of it as this red rectangle down at the bottom. It's actually a square. And this orange triangle above, right? So let me, with the orange turned on, turn off the red on and off for a second, and then same deal. If I turn on the red square, there's this orange triangle above. So we want to count those two things, and so that square, this red thing, maybe it was a rectangle, but it's actually a square. So the base is 10, the height is 10. For the triangle, so 1/2 times base times height, so there's the 1/2. The base is still 10. You see this across here. But the height is 50. Where did the 50 come from? We'll take a look at this point up there, where the y coordinate is 60. And then this point here, same x coordinate of 12. So since the x coordinates are both 12, to get this distance between these two highlighted points, it should be bigger y value of 60. Whoops. Bigger y value of 60 minus the smaller y value of 10. That's where this 50 right here, that's where that came from. But the other view of this is to, you could think of this same purple region. Here's the next Desmos link. You could think of this instead as, let me turn off this again. You can think of the big triangle, so that's shown here in blue, but you'll notice this big triangle, it accounts for all that purple region we saw, but it has this extra piece right there that you don't want. So we got to remove that piece right there. And how do we do that? So the big triangle, the one in blue, has a base of 12 and a height of 60. Okay, so 1/2 times base times height. But then we need to subtract this little triangle here, and this little triangle has a base of 2 and a height of 10. So 1/2 times 2 times 10. Hope it makes sense we're subtracting this, right? That I know it's not below the x-axis, so we're not thinking of negative area. It's just we computed too much area, and we just had to remove some. So, okay, I'll stop with talking and give you just maybe a moment to try. Maybe you already did that one, but I just wanted to talk through it and give you a moment to talk your way through some of these other ones. Could I go over number 5? Yeah. So number 5, the function here is y is equal to 2x minus 4. Now that's the graph of a line, right? So this is a, this y equal, hang on, I was typing out an email and I need to put this little glove back on in order for the writing to work out a little better. So y equals 2x minus 4 is the function. That's a line of slope 2 with y-intercept negative 4. So just as a rough sketch, negative 4 on the y-axis there. If the slope is 2, every time you move over 1 unit on the x-axis, you end up moving 2 units on the y-axis. So that should end up meaning that you should have an x-intercept of 2. So there's this line. You can also find this x-intercept of 2 just by plugging in y equals 0, right, into right here. And when you do that, you should end up with, yeah, the x coordinate is 2. But anyway, we're looking from x equals 1 to x equals 6 in this question. So look, the 1 has to be drawn to the left of the 2 and the 6 to the right of the 2, right? So we have this little triangle down there and this bigger triangle here. The bigger triangle is the positive area. It has a width or a base of 4, right? From starting at, if you start at 2 and you walk over to 6, that's going to be 4 units. The height, oh, I don't know yet. We need the y coordinate. Let's see. So you plug in 6 into there. So 2 times 6, 12 minus 4. So I believe 8. So I'm trying to do all this in my head. I shouldn't do that. I should just write it out. So 12 minus 4. Yeah, 8. Okay. And then the smaller triangle here, so let's get the y coordinate. When you plug in 1, so what's f of 1? So 2 times 1 minus 4, or 2 minus 4, that's going to be negative 2. So you have here a negative 2. So the bigger triangle, so in answer to this question, sorry for the arrow drawn, this link text is in the way. You have a positive area of 1/2 times a base of 4 times a height of 8 minus a 1/2 times a base of 1. That's this times a height of 2. So this might be all, come on. There we go. Sorry. New pen, right? Still trying to deal with how this thing works. So maybe I'll click on the link and maybe that'll be a cleaner picture of this. So again, there's that line. So I hope you got my explanation of why the x-intercept here is 2, but I wrote about it here as well in text form. So on paper, how do you find this x-intercept? Well, you can just plug in, to get an x-intercept, you should plug in y is 0. So back up here, I didn't show all the steps because it'll just get to be too much here, but you set y equal to 0 and y equals 2x minus 4. So you end up seeing that this orange triangle is positive area, has a width of 4, has a height of 8, as all of those things were just mentioned, right? 1/2 times 4 times 8. There's this little triangle down here in green, but it's a negative area with a width of 1. So this is from x equals 1 to x equals 2. That's where that, 2 minus 1 equals 1. And then the height is 2 from here to there. Those 2 points highlighted showing, yeah, right? So 1/2 times base of 1 times height of 2. So I hope that works as an explanation. That was a private conversation of could you go over number 5. Sorry, I should have maybe mentioned all that. But I actually would like to take a moment to just briefly talk through question 7. Again, I don't want to overdo it right now. I want you to actually click on all these links later and kind of go through. But no, please don't freeze. Okay, there we go. So to just talk through a little bit of question 7, the thing is to actually start with the hint. So x squared plus y squared equals 25 is a circle of radius 5. Right? So this also brings up some ideas from algebra that may have been forgotten, but there's the number over here is r squared, and so then the hint, starting with the hint and doing things right away, if you solve for y in this equation, sorry, I shouldn't have circled this. Now it's everything's a little bit of a okay. Y squared equals 25 minus x squared, and then when you square root both sides, technically when you square root, you have a plus or minus sign. Common error is people try to distribute the square root symbol, but you can't when you have a minus sign. So that's it. But here's the thing is, what's provided is y is equal to positive root 25 minus x squared. So this plus and minus actually makes sense to cover this top half and this bottom half, but the function that's over here is actually just the top half, because these are positive y coordinates. We have just y is equal to root 25 minus x squared, so not the negative side. So it's really just the top half of the circle. Or let's do this. I think here as well, I figured the link this one might be helpful, right? So first of all, there's the entire circle. So let me turn off this thingy. The entire circle shown in red, x squared plus y squared equals 25. You'll see even in the picture that the radius is 5. And then I'm going through the algebra steps here. You see in part 2 this subtracting x squared on both sides, and then square rooting both sides. I couldn't get the computer to do it right, but so I just wrote in plus and a minus sign. So sorry for how that looks. But we were asked about y is equal to just the plus square root of 25 minus x squared, and that picture. So this should be a function, right? Vertical line test needs to pass. That's the top half. That's when the y coordinate is positive. The thing is, this is half. So if you look, we were asked about the integral from -5 to 5, and that actually is right there to there. This is half the area of a circle. So recall we did review the area of a circle, pi r squared. So you take the area of a circle, pi r squared, so pi times 5 squared, and then we need to take the area of that circle and only count half of it because we only have half the circle. So 1/2 times pi times 5 squared is our answer. Sometimes the error that people make, the common error, is that people take the radius and cut it in half for some reason. So if you do that, you'll get a different number. So if you take the radius of 5 and you divide by 2, and you call that your new radius, okay, then you take that and you square it, and then you multiply by pi. That's a different number. That's the area of an entire circle whose radius is cut in half. That's a circle of radius 5 halves. That's different than. So what thing do you cut in half? Well, we cut the area of a circle of radius 5 in half. Over here, this incorrect answer, where you see this not, that's the full circle of radius 2.5. That's a different thing. Just compute it, try it in a calculator. You'll see that this number and that number are different. Okay, that's all I kind of want to say about that right now. You just need to try that out to see. What we're going to do, having tried, I hope, some of these, and I hope you'll click on these links later to check on what the pictures look like. But the whole point of all of these questions is to say these are about signed area. And so there are a couple properties I want to talk through about signed area. Now these properties look a little strange, and I will comment that there are some web work questions that allow you to practice and exercise these. Now I want to just talk through some of these. The first property here, doesn't even matter what function you have, but when you look at the area starting at x equals a, and yeah, this is not a typo, ending at x equals a. I know it's normally starting at x is a and then ending at x is b, like the second formula, but if you start at x is a, so here's some function. I just, in a cartoon form, there's some function down there at the bottom. Starting at x is a, start there, and then end at x is a. So what does that do? It creates this triangle that's very thin. Like the height is dependent on what f of x is, but it doesn't matter because the width, if you start at x is a and you end at x is a, think about this as an area. This rectangle is very thin. I mean, so like the width is 0, and if the width is 0, start at x is a and end at x is a, that overall area is going to be 0. That's where that 0 comes from. For the next property, this is just a little strange kind of on its own, but if you have an a here and you have a b there, sometimes you need to swap. And so if you swap and you put the a up there instead and the b down here, the only thing you need to do when you swap where those go is the cost of that swap is a minus sign. We'll see an example of this in a moment. Um, so this property number 2 doesn't make much geometric sense, and it's not supposed to. It's just a thing that we need on a practical level for what we do tomorrow and next Monday. But yeah, the cost of taking where the a and b are located and swapping them is you need to introduce a minus sign. The third property, we actually did see one like this for indefinite integrals, or remember indefinite integrals from earlier, that's for antiderivatives. When you have a constant times your function, you can bring the constant in front of the integral sign. So, and then property 4 looks like one that we've seen for indefinite integrals. So there's a definite integral version of it, so that when you're integrating and you've got one function plus another, you can split it up into two smaller integrals. And same for a difference, you can take the integral of the difference of two functions and split it up as two separate integral problems over here. So it's the same sort of thing we saw with indefinite integrals, just for definite integrals. That's what properties 3 and 4 are all about. Property 5, there's no version of this for indefinite integrals. The property 5, I promise this will make sense if you just think about this definite integral right here as being an area. So I have a picture that will help. I think it's actually very convincing. Property 5, there's just some function. So I just, in a cartoon, just drew some wavy function. Just some function. Okay, it doesn't matter really which function. And then here, it's just an area starting at x is a and going up to x is c. I just, to start, drew in 3 x values in order. A, B, C. Just left to right. A, B, C. Like that. And so then the area from A, x is A, and ending at x is C. So I won't shade it in quite yet, but that's what the left side here represents. And the point is, we haven't not even used a B yet, but you can break this up by having this sort of B in the middle somewhere. And so it's the area from A to B, that's this part, that's circled here. And then you add to that the area from B to C, and that's this second shaded part. That's all this fifth property is trying to say. And there's a lot, I think, to take in. And these, properties 3 and 4, anyway, were just, I appealed to things that we've seen for integrals without the numbers listed on them, for indefinite integrals. Property 1 we talked through, and property 5 we talked through, but it's a little too generic just like that. I think it's a little more helpful if we look at actual examples of how to use this, and you'll see WebWork questions that do the same. Now, in this question, I wanted the properties still listed up at the top so we could see, but you've got integral from 2 to 7 of f of x dx, and we're told that this is 10. So we weren't even given the function here, okay? It's just some mystery function f of x. But we're told that if you, the area under that function, or the area under the function and above the x-axis, starting from 2 and ending at 7, is 10. We're just told the signed area is 10. Now we're asked to find the integral from 7 to 2 of 3 times f of x dx. Now you'll notice where the 7 and 2 are located are swapped. So this is, I'm trying to create an excuse question where we can practice property number 2. So what I did was I recopied the question part over here. We were given information, but I have here integral from 7 to 2 of 3 times f of x dx. There's a couple different ways you can work through this, but I just want to stick to the order I have here in my slides. Okay, there's other ways to do this, but I'm going to start by swapping the location of the 7 and the 2. So you'll notice what's different from here to here is instead of the 7 below and the 2 above, now the 2 is below and the 7 is above. But the cost of that swap using property 2, in addition to just swapping where A and B are located, the only other difference is you need to introduce a minus sign. So that's what this minus sign here is about. Okay, so this is applying property number 2. The other thing I want to do is I'd like to move this 3. It's like right here, that's a constant k, and I'd like to bring it in front of the integral. So the minus sign I'm going to still copy. So this minus sign right there is just copied right there. But then the only other difference is instead of having the 3 within the integral, I wrote the 3 just in front of the integral. So you'll notice 3 is located there instead. The whole point of doing this is that you'll see then, take a look at this part right here. Why all that manipulation? This part circled here, the integral from 2 to 7 of f of x dx. We were given that, right? So yeah, the minus sign came from formula 2, and then the 3 we brought in front, but this thing in red, we were told right here, this information, that that is equal to 10. And so that right there got replaced with a 10, and then just to simplify the work here, this ends up being negative 30. Step back one step here. The final answer is negative 30, but the key step here is we kept applying some of these other formulas so that we could eventually make use of this information we were provided. We were told that the integral from 2 to 7 of this function we don't even know is equal to the number 10, and this kind of manipulating these different properties together gave us a way to use this. I have one more like this just to illustrate especially the strange property number 2. We can apply this property even when we were not told what specific function, but we were given just enough info to answer the question. We can also do this property too when we are told the function. So same 5 properties up there. I'd like to look at the integral from x equals 5 to x equals negative 1 of the function 4x dx. Now this is a little unusual how the question is, because we're provided the function, and normally the smaller x value is down here and the bigger x value is up there. In fact, earlier today, the first question today was we looked at the integral of this function 4x from x equals negative 1 to x equals 5. So you'll notice the two x values are swapped in location, and we found, at least when the x value is down, the smaller x value is down here and the bigger x value is up there, this is assigned area, and we had this number 48 as the final answer to our first question. But because the two x values are swapped, we'll apply this property number 2, and the cost of swapping to have the negative 1 up here instead and the 5, the bigger x value, down here instead, the cost of that swap is, instead of having a 48, we have to have a negative 48. So I know that's a little, I wanted to illustrate especially this property in number 2 because it's sort of the strange one, but you can kind of see we tried properties 2 and 3, and I think that's usually just about the right amount of stuff to see what's going on sort of with and then you'll see these properties kind of pop up where you'll need to use these in homework. The key thing I want to remind you though is that indefinite integrals, that is a part of exam 4, while this new thing, definite integrals, is not on exam 4. And I know this split of stuff is always a little challenging. Just please note that when it comes to exam 4, you have indefinite integrals, and that's an antiderivative problem. Whether you do substitution or not depends on the problem, but here, just without substitution, the antiderivative is x squared plus c, whereas this new thing, the definite integral, the final answer is a number, and it represents signed area. The area of this region is 36. Now these, it just seems so strange that these things have very, very similar notation, and it seems almost confusing, but there's a reason for it, and tomorrow we look at why. What is the connection between these two problems? It seems like there's no connection at all. And tomorrow we actually talk about this thing called the fundamental theorem of calculus. It brings all the main concepts of calculus together, and it connects why anybody would even bother using similar notations for both of these. What happens actually really tomorrow is we've been looking at this problem type right over here, the definite integral, as an area problem, and that's a good way to think of it because it's the original way to think of this. But tomorrow we will actually compute areas without using area formulas. We'll have a new way to do this tomorrow. So again, just a reminder, please do. The key thing is the online quiz today and the pre-exam assignment due Wednesday. And I think we'll call it with that, unless there's a question. Well, I'll stop the recording in any case.